Hey there everyone, Adrian again here, and in this third video about chemical bonding, we're going to be talking about formal charge and resonance structures. So these are two more advanced bonding topics, but they're also very important in our study. So let's get right into it. Let's talk a little bit about what formal charge is and why it's important. So formal charge is the charge that's assigned to an atom in a molecule disregarding relative electronegativity. So we talked a little bit about electronegativity in the last video. Electronegativity determines where the electrons are being hogged towards in a bond. The more electronegative atoms, such as fluorine, nitrogen, and oxygen, will tend to pull the electrons closer to them in a chemical bond. But in formal charge, it assumes that all bonds are nonpolar covalent bonds. So conventions for determining formal charge means that the most favorable structure of any molecule will have atoms that have a formal charge of 0. If that's not possible, the closer the charge is to 0, the better, and I circled this because it links back to our study of electronegativity. The most electronegative atom should have the most negative formal charge. In next videos, I'm going to be talking about exceptions to the octet rule, and this rule comes up in determining why it's important, or why the octet rule is violated in an incomplete octet, or an expanded octet, for example. So let's talk about examples of formal charge, or using formal charge. So the thiocyanate ion, SCN-, is a perfect example of a polyatomic ion that has multiple structures, and we can draw them using the same rules that we used for Lewis dot structures in the previous video. So we know in our periodic table that sulfur has 6 valence electrons, so it's 6, carbon will have 4, nitrogen will have 5, and then because it's a polyatomic ion, we're going to have to bring down this charge and add 1 more electron, so this is 6, 10 plus 6 equals 16. We have to show 16 valence electrons in any valid structure of the thiocyanate ion. So there are actually multiple ways to draw this structure, but not all of them are the most common or most predominant, and we can determine what is based on formal charge. So as I said before, when we're drawing Lewis structures, the most electronegative atom will be in the center, which is often carbon. So let's draw SCN. Let's link them using single bonds. And let's count our current number of electrons. We have 6 here, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So we currently have 20, but we need 16. So we're going to have to eliminate 2 of these lone pairs that are attached to the atoms and instead share them between the atoms, between the 2 atoms or 3 atoms in the compound. So what's one way we can do this? We could cross out these lone pairs here and make a triple bond here. So if I rewrite our structure, that would look something like this. With no lone pair on the central carbon. This is our first structure of the thiocyanate ion. We could do the exact same thing on the other side. We could cross out these 2 lone pairs again here and make a triple bond here. So rewriting that, that would look like this. We have a single bond to the sulfur, no lone pairs on the central carbon atom again, but we are triple bonded to the nitrogen atom on the right side. Then the final way is, I'll just rewrite this again up here, SCN, pair, single. We could also make a double bond on both sides of the central carbon. Central carbon, double bond, no lone pairs yet again. And instead we have 2 lone pairs on either of the outer atoms. So which one of these structures is most predominant? The way we determine this is using formal charge. The way to calculate formal charge, the easiest way that I use, is to take the number of normal valence electrons, NVE is the way I abbreviate it, minus the electrons owned in the structure. What I mean by that is, remember, we're assuming the electronegativity difference does not matter, so that each atom would equally take one electron, from one covalent bond. So that means that this covalent bond, for example, which contains 2 electrons, one of those electrons will go to the sulfur, one to the carbon. So you just take the number of bonding electrons here and divide it by 2 to assign it to an atom. So let's take sulfur here as an example. So the number of normal valence electrons we said is 6. So it would be 6 minus the electrons owned. So 1, 2, 3, 4, 5, because we're dividing by 2. 6 by minus 5 is positive 1. Then let's do the same for carbon. Carbon has 4 valence electrons. 1, 2, 3, 4 electrons owned in the structure. 4 minus 4 is 0. 1, 2, 3, 4, 5, 6, 7. So nitrogen has 5 valence electrons. 5 minus 7 will give us negative 2. So as we talked about in our conventions of formal charge, this is not very favorable because negative 2 is not close to 0. And even though nitrogen is the most electronegative element in this structure, it's still not favorable at all. So let's take a look at the other structures that could be the predominant structure. Let's do the same thing here. Sulfur with 6 normal valence electrons, 6, and then plus 1 is 7. 6 minus 7 is negative 1. Same thing here. Carbon will have 0. Then this will also have 0, because 1, 2, 3, 4, 5, 5 minus 5 will give us 0. So this looks pretty favorable. It's better than plus 1 and negative 2. But remember, again, for rule number 3, the most electronegative atom should have the most negative formal charge. And nitrogen is much more electronegative than sulfur is. So let's take a look at the last structure with 2 double bonds. 1, 2, 3, 4, 5, 6, give us 0. 0 again. 1, 2, 3, 4, 5, 6. 5 minus 6 is negative 1. So this will be the predominant structure for the thiocyanate ion. Why? Because it follows our formal charge conventions the best. The formal charges are almost 0 with the exception of this one negative 1 formal charge on the nitrogen, and the most electronegative atom, in this case the nitrogen, is assigned the most negative formal charge. So this is the most favorable structure for us for the thiocyanate ion. So we're going to talk about another subject very closely related to formal charge, which is resonance structures. Resonance structures. We saw that there were multiple ways to draw the Lewis dot structure for the thiocyanate ion, or in resonance structures, the formal charges for multiple forms of the same molecule are equally favorable. So a good example of this is NO2-. So this polyatomic ion is called the nitrite ion, and we can draw it like this. Let's see, we need how many valence electrons? So N will have 5, we'll bring this here, will give us plus 1 is 6. Then O has 6 valence electrons times 2 because it's O2 is 12. 6 plus 12 gives us 18 valence electrons that we have to show in our structure. Let's draw our bonds. Lone pairs to complete octets. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So we currently have 20 valence electrons and we have to get down to 18. Simply we can share one of these lone pairs instead of assigning them to an atom. So I could share this lone pair here, and that would give me one structure which would look like this. And then this would have the same single bond. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Sorry, this looks like a stray mark, but it's not really. It's nothing, it's not supposed to be anything. So 18, this should be a predominant structure, right? Well, can we do the exact same thing on the other side? We could cross this out and give us another double bond, and this would become a single bond. What if we do that? We have 6 valence electrons here, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. These both have 18 valence electrons. So what would we do? Let's look at formal charge. So oxygen will have 6 valence electrons minus 6 electrons that it owns, 0. 5 owned electrons, 5 valence electrons, also 0. Then it owns 7 electrons. It normally has 6, so 6 minus 7 is negative 1. Then we can apply the same thing here. Owned 7. 6 minus 7, negative 1. Owns 5. 5 minus 5, 0. 6 minus 6 is also 0. So because oxygen is the most electronegative atom here, it seems like both structures would be equally favorable. So this is what a resonance structure is, equally favorable in terms of formal charges. But is the actual structure of the nitrite ion anything like this? Well, it's actually in between. The length of these bonds, this is not an actual double bond. Why? Because we could easily switch it based on where we wanted to put the electrons. We could do this arbitrarily for any for any molecule that exhibits resonance. So the actual length of the bonds, it can be determined by bond order. So bond order is the number of bonds. So let's count 1, 2, 3. So 3 bonds divided by the number of non-central atoms, or the atoms around the central atom. So we have 1, 2, 2 atoms. This gives us a bond order of 3/2. Now, what does this exactly mean? This means that the actual bonds in the nitrite ion will be not single bonds, not double bonds, but rather 3/2 bonds. The length of the bonds in the nitrite ion will be directly in between single and double. This is a limitation of Lewis structures. Lewis structures can't correctly show the length of bonds in resonance structures, so we have to use bond order to determine the correct lengths. So another example of a molecule that exhibits resonance is ozone, which is a big part of our atmosphere. So O3, it has no charge, so we can just say 6 times 3. We'll again need to show 18 valence electrons. So that's 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So again, we could do the same thing. We could either cross this out, form a double bond here, or cross this out and form a double bond here. Both of which, according to formal charge, will be equally favorable. So with a double bond on the left side, our structure for ozone would look like this, with no charge up here because it's a neutral molecule. Or, flip to the other side, in terms of formal charge will give us 0, then 6 minus 5 will give us positive 1, and then here we have 6 minus 7 will give us negative 1. Same principle here, we have 6 minus 7, 1, 2, 3, 4, 5, 6, 7, give us negative 1. 1, 2, 3, 4, 5, 6 minus 5 will give us positive 1, and this will give us 0. They're equivalent, they're equal, they're both pretty unfavorable, but they're equally favorable in terms of formal charge. So let's calculate the bond order. The bond order for ozone will give us 1, 2, 3 bonds, divided by 2 non-central atoms. It's the same bond order as the nitrite ion, with a bond order of 3/2. Not single, not double, but 3/2 bonds instead. So in this video we learned about formal charge and how to assign formal charge to an atom to determine a predominant structure in molecules that do not exhibit resonance, and we learned how to determine the actual length of bonds, the bond order, in resonance structures in molecules that do exhibit resonance, such as the nitrite ion and the ozone molecule. In the next video I'll cover exceptions to the octet rule, and we'll begin talking about molecular geometry. I'm going to split molecular geometry into 2 separate videos because it's such a large topic. Alright, thank you, goodbye.